Why do unstable particles have to decay at all, instead of just staying the way they are forever? Think about what happens when you grab a spring, bend it into a weird twisted shape, and then let go. It snaps back towards its natural form. And that extra wrong tension turns into a series of fine jitters that slowly die out. In the energy filament theory, particle decay is exactly that kind of spring rebound happening in the microscopic world. A particle is a short segment of energy filament that has been wounded up, tightened and closed into a small ring. If the ring is wounded in an easy, low-cost way, and its internal rhythm lines up well with the background rhythm of the energy sea, it can live for a very long time. That is the story of stable particles like electrons and neutrinos. Unstable particles are different. They are like springs you have forced into a strained, ugly pose that looks okay for a moment but is quietly storing trouble. Their awkwardness shows up in three main ways. The first is directional awkwardness. The energy sea itself has preferred large-scale flow patterns, like big slow currents in an ocean. But the small ring's internal circulation may be running against that current or at a sharp angle to it. That makes the particles feel like a tiny boat trying to go upstream forever. The surrounding waves keep pushing and shaking it. And the longer it stays that way, the harder it is to maintain its original orientation. The second is shaping awkwardness. Some ways of winding the filament cost far more tension than others. It is like pinching and twisting a spring into a very uncomfortable configuration and having to keep your fingers pressed hard just to hold it there. As soon as there is a little disturbance from outside, or the grip provided by the surrounding pattern slips even slightly, that high-cost shape naturally starts to slide towards a lazier, cheaper winding. The third is rhythm awkwardness. The internal flow around the ring has its own beat, and the energy sea as a whole has its own tension rhythm. If these beats clash badly, it is like two dancers on the same floor hearing different music. One stepping in 3 beat, the other in 4 beat. Their feet never land on the same counts. And over time, this mismatch builds up as a kind of internal stress that is always looking for a way out. When directional, shape and rhythm awkwardness pile up together, you get what we can call a generalized unstable particle. Something that can be held together for a short while but is, in spirit, a forced bent spring waiting for its chance to release. Once the stored awkwardness crosses a certain threshold, the structure can no longer pay the cost of staying twisted. It collapses out of its tight, expensive configuration and rapidly rearranges into a set of easier, cheaper windings. This is the microscopic version of the spring snapping back towards its factory shape. The extra tension does not vanish. It pours into waves, along the filament ring and into the surrounding energy sea. The surplus strain becomes a series of outward pushing ripples, like packets of disturbance peeling away from the original spot and flying off. What our detectors register as decay products and released energy are just these news, cheaper filament rings plus the wave packets that have carried away the excess tension. From this perspective, decay is not a particle suddenly breaking or being punished. It is a tight, high-tension structure being refitted into lower-tension structures, with the leftover strain exported as traveling waves. In mainstream physics language, this whole process is grouped under the weak interaction, treated as one of the basic forces of nature that can change one type of particles into another and shuffle entire families of particles in a regular pattern, often drawn as lines and vertices in a Feynman diagram. In the energy filament theory, the weak interaction is not a separate new force layered on top of everything else. It is the visible face of the spring rebound pattern. Whenever a filament ring has been wounded in a way that is too costly in direction, shape and rhythm for the energy sea to tolerate forever, as long as the configuration is awkward enough, the energy sea wants to let it fall back towards smoother, cheaper shapes. And when we glance at that process from the outside, we give it the familiar name of particle decay. In this season, you only need to hold on to the picture. An unstable particle is a bent spring that has been forced out of its comfort zone. The detailed rules which particles are allowed to rebound, which paths they may take when they do, and which combinations are strictly forbidden belong to a deeper playbook that will be unfolded in a later season. For now, one sentence can close the loop. Unstable particles decay not because something far away pulls a secret string, but because they themselves are overbent springs, and given a little time they snap back, turning their stored, uncomfortable tension into rings and wave packets that race away through the energy sea. Tap follow, share it on New Physics, Clear Universe.